Hi everyone, my name is Nia Shazami and welcome to my presentation on circuit simulation and analysis. In this project, we review several popular circuit simulation tools including LTSpice, Protos, Multisim, PSpice, MATLAB Simulink, and KiCad. However, for the practical part, we focus on LTSpice and show how to design, simulate, and analyze circuits using it. This project is prepared for Dr. Sadili's Electrical and Electronic Circuits course at Firdaus University of Mashhad. And let's get started. So, why do we even need circuit simulation? Well, modern circuits are becoming more and more complex, and navigating these intricate designs can be challenging. Building a physical prototype for every design is expensive and can take a lot of time, of course. It also comes with risks because errors in design might only show up after you've built the circuit. This is where pre-hardware simulation comes in. By simulating circuits virtually, we can catch mistakes early, test different scenarios, and save both time and resources. In fact, mastering circuit simulation is an essential skill for any electrical or electronics engineer, and it's a core competency for success in both academic projects and real-world applications. Now that we understand why circuit simulation is important, let's talk about the tools themselves. Circuit simulation software is designed to virtually model and test circuits before building them physically. When comparing these tools, there are several key factors to consider. First, computational speed. How fast the software can run simulations. Second, simulation accuracy, ensuring the results are reliable and reflect real-world behavior. Third, component libraries, the availability of a wide range of components for your circuits. Fourth, types of analysis. Some software can handle DC, AC transient, or even frequency and harmonic analysis. Finally, ease of use. An intuitive and friendly design environment helps you focus on learning and experimentation rather than struggling with the software. By considering these factors, you can choose the right tool for your project, whether it's for learning, research, or industrial applications. Now, let's take a quick look at some of the most popular circuit simulation tools used today. First, we have LTSpice. It's a free and very fast spice-based simulator mainly used for analog and power electronics circuits. Next is Protos. Protos is especially popular for embedded systems because it allows you to simulate both the circuit and the microcontroller code at the same time. Multisim is another well-known tool widely used in education. It has an easy-to-use interface and supports both analog and digital circuits. Then there is PSpice, developed by Cadence. It's an industrial-grade simulator known for its high accuracy and is commonly used in professional designs. We also have MATLAB and Simulink, which is powerful for system-level modeling and multi-domain simulations rather than detailed circuit-level design. And finally, there is KiCad. It's a free and open-source tool which is mainly used for schematic capture and PCB design with basic SPI simulation features. When we compare these tools, several important differences stand out. One key factor is the licensing model. Some tools, like LTSpice and KiCad, are completely free, while others, such as PSpice and MATLAB, are commercial and require a license. Another factor is the application focus. Tools like Multisim are more suited for educational purposes, while PSpice and MATLAB are often used in industrial and professional environments. Each software also has its own strengths and limitations, some excel in accuracy, some in ease of use, and some in system-level analysis. Okay, now let's focus more on LTSpice. LTSpice is a free circuit simulation software developed by Analog Devices, and it is based on the SPICE simulation engine. One of the main advantages of LTSpice is that it is completely free with no limitations on circuit size or number of components, which makes it very popular among students and engineers. This software is especially optimized for analog and power electronics, such as amplifiers, filters, and switching power supplies. LTSpice is known for its high simulation speed and good numerical accuracy, even for complex analog circuits. Because of these features, it is widely used in both academia and industry for circuit analysis and design. However, LTSpice also has some limitations. It is not suitable for complex digital circuit simulation, and it does not support PCB design since it focuses only on schematic level simulation. Alright, so in this part of the project, I will show how to install LTSpice and how to use it for basic circuit simulation. First, we go to a Visual Analog Devices website and download LTSpice. Since I am using macOS, I select Download for macOS and wait for the installer to finish downloading. After opening the downloaded file, the installation process is very straightforward. I click on Continue, accept the license agreement, and then choose Install. Once the installation is completed, LTSpice will be available in the Applications folder. After launching LTSpice, we start by creating a new schematic. From the top menu, I select File and then New Schematic. This opens a blank workspace where we can design our circuit. To add components to the schematic, I right-click on the workspace and choose Draft and then the component. A component selection window opens where I can search for different elements such as resistors, capacitors, diodes, or voltage sources. After selecting a component, I simply click on the schematic to place it. To modify a component's value, for example the resistance or capacitance, I right-click on the component and enter the desired value. Next, we need to connect the components using wires. From the menu, I select Draft, Wire, and then draw wires between the component terminals. It is important to make sure that all components are properly connected, otherwise the simulation will not run correctly. Before running the simulation, we must define the type of analysis. This is done by selecting Draft, the Spice Directive, and entering the required command. For example, for transient analysis, we can use the .trend command and specify the simulation time. After placing the directive on the schematic, the circuit is ready for simulation. To run the simulation, I click on the Run button, which is represented by a running man icon. Once the simulation starts, a waveform viewer window opens, where we can observe voltages and currents in different parts of the circuit by clicking on the nodes or components. Okay, now let's look at a practical example, a rectifier circuit with a filter capacitor. In this example, we use an AC voltage source with an amplitude of 10 volts and a frequency of 50 Hz. Then we add a diode using this model, followed by a resistor with a value of 1 kilo-ohm and a filter capacitor of 100 microfarads. To observe the ripple at the output, we perform a transient analysis using the command .trend. After running the simulation, we can click on the output node to observe the voltage waveform. From the waveform, we can clearly see the rectified signal and the effect of the filter capacitor in reducing the ripple. This example demonstrates how LTSpice can be used to analyze real circuit behavior before building the physical circuit. In conclusion, circuit simulation plays a very important role in modern electronics design. With increasing circuit complexity and development costs, simulation allows engineers and students to analyze and verify circuit behavior before building the actual hardware. In this project, we compared several popular circuit simulation tools and discussed their strengths and limitations. This comparison showed that each software is suitable for specific applications depending on accuracy, usability, and target domain. We then focused on LTSpice and gained practical experience in installing the software, designing circuits, running different types of analysis, and interpreting simulation results. One of the main advantages of simulation is that it reduces design errors, saves time and cost, and helps identify potential problems at an early stage of the design process. Finally, circuit simulation is a key skill for future academic studies and industrial projects as it bridges the gap between theoretical knowledge and real-world implementation. Alright then, this brings us to the end of this presentation. I hope this explanation was helpful in understanding how simulation can be used to analyze circuits efficiently before hardware implementation. Thank you for watching.